Hello, and welcome to the review video for STA 301 Module 10. The big picture idea in this module is that we looked at how to compare the means from two or more samples. First, we looked at descriptive statistics for two samples. I showed you some basic numerical summaries and graphical displays that can be used to gain insight into your data when you have more than two samples. In real life, when working with real data, you'll often have much more than information regarding a single sample, so it's important that you understand how to summarize data that is bivariate in nature, or just more than one sample. A really useful graphical display that was presented was a comparative box plot. You can gain quite a bit of information about your different distributions based on looking at a comparative box plot. So it's important that you're able to read that graphical display and draw conclusions from looking at it. Be sure in this module that you can read and interpret RStudio output. That includes indicating the form of the alternative hypothesis. Remember, our alternative hypothesis can take three different forms depending on the purpose of the test. We can either have a less than sign when we're running a left-tailed test, a greater than sign when we're running a right-tailed test, or a not equal sign when we're running a two-tailed test. I discussed extensively in Module 9 how to determine the form of the alternative hypothesis. It's also important to recognize which procedure has been implemented. You need to understand which arguments within the RStudio code, and oftentimes within the same function, allow you to differentiate between the different procedures that were presented here in Module 10. Another big idea from Module 10 is that you need to understand how to interpret a confidence interval for the difference between two population parameters. It's imperative that you pay attention to which is sample 1 and which is sample 2. It doesn't matter what you put as sample 1 or sample 2, but you've got to know what you did and pay attention to it when it comes time to interpret the confidence interval for the difference between the two parameters. Remember that if all the values in the confidence interval for the difference between two population parameters are positive, that interval then suggests that the first parameter is bigger, and your interpretation needs to reflect that. If all the values in the confidence interval are negative, on the other hand, then the confidence interval suggests that the second parameter is bigger, and your interpretation needs to reflect that. If 0 falls within the confidence interval, then it's inconclusive. Either the first parameter could be bigger, the second parameter could be bigger, or there could be no difference between the parameters because your confidence interval includes the value 0, as well as negative values and positive values. So in summary, when you are interpreting a confidence interval for the difference between two population parameters, your interpretation must correctly reflect which population parameter is bigger or smaller and by how much. In Module 10, one of the big things when you're comparing means from two samples, first thing you need to do is identify, do you have independent or dependent samples, because that will guide your choice of procedure. Independent samples, it's just what it says. There's no natural pairing, no dependency, no relationship between the elements of either sample. And so, if you have independent samples, you can use either the pooled or non-pooled procedures. If you have dependent samples, aka samples where there is some type of natural pairing or relationship, any kind of before and after measurement, any time when you have measurements taken on the same subject, anything like that, then you have dependent samples and you have to use the paired procedures. So a big punchline from Module 10, first and foremost, can you identify whether or not you have independent or dependent samples, and based on that information, what do you do with it in terms of selecting a procedure? If you have independent samples and you wish to compare the means from two independent samples, you can use either the pooled or non-pooled procedures. To reiterate again, both are used with independent samples. How do we determine whether to use the pooled or non-pooled procedures? Well, you have to look at the ratio of the sample standard deviations. When computing the ratio of the sample standard deviations, always put the value that is larger in magnitude on top. So if this ratio of the larger in value sample standard deviation divided by the smaller in value sample standard deviation is less than 2, then we use the pooled procedures. And it's reasonable to assume that the population variances are approximately equal. Otherwise, we have to use the non-pooled procedures because it is not reasonable to assume that the population variances are approximately equal. Both of these are implemented within RStudio by using the t.test function. The pooled test and confidence interval is what we use when it's reasonable to assume the population variances are approximately equal, as I just explained. you want to look for the argument var.equal equals true within the RStudio code. That's how you tell RStudio, hey, I want you to run the pooled version. The default in RStudio is to run the non-pooled version, which makes sense. The non-pooled test and confidence interval is what we use when it is not reasonable to assume the population variances are approximately equal, as I explained. When reporting the number of degrees of freedom for the non-pooled t-test, you always round down to a whole number. You will probably get a decimal, and that stems from the formula that is used to compute the number of degrees of freedom in the non-pooled scenario. This will not include the argument var.equal equals true. The default is var.equal equals false. So if you leave out that argument, you will get the non-pooled test. On the other hand, if we are working with dependent samples, then we use the paired procedures. And once again, dependent samples are samples that have a natural pairing, oftentimes two measurements taken on the same subject. This is really analogous to running a one-sample t-test on the differences. You'll see that reflected in the number of degrees of freedom. It's n-1. So the paired t-test is really just running a one-sample t-test on the differences as we learned in Module 9. In order to run the paired t-test or construct a paired t-interval, you've got to have the argument paired equals true within the RStudio code. Now, what if we want to compare the means from more than two independent samples? Well, fortunately, we have what's called one-way Anova, and that is a generalization of the pooled t-test. It is important that you understand the logic of one-way Anova, the idea that we compare the between variation to the within variation. In other words, there's variation between the sample means, and there's also variation just within the samples themselves due to sampling variability. Well, our test statistic, which is an F-test statistic, looks at the ratio of the between variation to within variation. If the between variation is very large compared to the within variation, then that ratio is going to grow. That value from the F distribution is going to get pushed further and further into the right tail of the F distribution, which means the area to the right of it will be smaller and smaller and smaller, and so our p-value would be small in that case, which would serve as evidence against the null. And so once again, it's important that you understand the logic of one-way Anova, the idea that we're comparing the variation between to the variation within. After all, one-way Anova stands for analysis of variance. The hypotheses in general for a one-way Anova, our null hypothesis is that all the population means are equal, and our alternative is that not all the means are equal. Remember, that does not mean that they necessarily all need to be different. It just means that they're not all the same. Your hypotheses for a one-way Anova must be written in this way. Remember that we have the Tukey multiple comparisons procedure is what we use as a follow-up to a statistically significant result for a one-way Anova. Oftentimes, it makes sense that we would want to know, okay, if we know that not all the population means are equal, well, which ones differ? And that's where we come to Tukey multiple comparisons to help us answer that question. In terms of assumptions for inferential procedures, there are assumptions for any inferential procedure that must be satisfied in order for the results of that inferential procedure to be valid and meaningful. And so there were assumptions presented for all of these inferential procedures here in Module 10. Make sure that you are familiar with those assumptions so that you understand what needs to be satisfied in order for the results of the statistical inference to be valid and meaningful.